Hi, I'm Bob. Welcome back to the 5 Minute Econometrics, an econometric tutorial on basic concepts, identification strategies, and estimation approaches. Today, we will investigate what the blue estimators are. The term blue is an acronym for the best linear unbiased estimator. The OLS estimators are the best linear unbiased estimators, that is, the blue estimators, under the Gauss-Markov assumptions. In other words, estimators using the ordinary least squares method have the smallest variance among all linear unbiased estimators under the following 5 assumptions: linear in parameters, random sampling, no perfect collinearity, zero conditional mean, and homoscedasticity. This result is called the Gauss-Markov theorem in econometrics. A blue estimator is a linear estimator. A linear estimator can be written as a linear function of the data on the outcome variable, where the matrix W is a function of explanatory variables. We can see the OLS estimators are linear from its expression. Second, a blue estimator is an unbiased estimator for the population parameters. The unbiasedness of the OLS estimators relies on the first 4 Gauss-Markov assumptions. The zero conditional mean assumption is the key assumption for the unbiasedness. Here is the proof. We need to prove the expected value of the OLS estimator beta hat conditional on the explanatory variable x equals the population parameters beta. In the first step, we substitute the population model equation y equals x multiplied by beta plus mu into the OLS estimator. And find that the first term is the population parameter beta. In the second step, we find the expected value of beta hat conditional on x. Because of the zero conditional mean assumption, the expectation of the OLS estimator equals the population parameter. That is to say, the OLS estimator is an unbiased estimator for the population parameter. Third, a blue estimator has the smallest variance among all linear unbiased estimators. The word best means the estimators have the smallest variance. Estimators with the smallest variance are also called efficient estimators. All 5 Gauss-Markov assumptions are needed for the OLS estimators to be the blue, best linear unbiased estimators. Here's the proof. In the first step, we write the variance of the OLS estimator, beta hat. In the second step, we assume another linear unbiased estimator, beta tilde. It is a linear estimator, so it is a linear function of the outcome variable y, where A is a matrix of the explanatory variables. Substituting the population model equation for y leads to 4 terms. Next, we use the property of unbiasedness to simplify it. We write the expectation of beta tilde. The last 2 terms are 0 because we assume the error term is not correlated with the explanatory variables. Since beta tilde is an unbiased estimator, its expectation should be equal to beta. It leads to an important result. Matrix A multiplied by matrix X equals 0. Using this result, we can simplify the beta tilde into 3 terms. In the third step, we calculate the variance of beta tilde. The parameter beta can be seen as a constant and its variance is 0. We focus on the last 2 terms. We write them as a constant matrix times the random error term. The variance of a random vector mu multiplied by a constant matrix is as follows. We know the variance of mu equals sigma squared. We then use the result from the previous step to simplify it. Finally, we conclude that all other linear unbiased estimators have larger variances than the OLS estimators under the 5 Gauss-Markov assumptions. We first use simulated data to show that when the zero conditional mean assumption is satisfied, the OLS estimates are closer to the parameter than the case when the zero conditional mean assumption is not satisfied. Then we use real-life data to show if the homoscedasticity assumption is not satisfied. The OLS estimators no longer have the smallest variance. Weighted least squares estimators could have smaller variances. We generate simulated data in Stata. We first set the seed and the observation number, and then use the random number function to generate the explanatory variable x, which is randomly drawn from a standard normal distribution. Setting the seed is crucial to ensure that we obtain the same random numbers each time we run the program. Then we generate 2 error terms, mu1 and mu2. mu1 is uncorrelated with the explanatory variable x, and mu2 is correlated with the explanatory variable x by construction. Next, we create 2 outcome variables, y1 and y2, that correspond to the 2 error terms. We assign the intercept and slope coefficients as the 2 parameters. These are the 2 relationships between y and x. So we have simulated data with specific features, allowing us to determine whether OLS estimates are unbiased. We regress y1 on x and find that the estimated coefficients are close to the 2 values we set. We regress y2 on x and find that the estimated slope coefficient is far away from the 2 value we assign. The reason is that the data generating process for y1 satisfies the zero conditional mean assumption, but that for y2 does not. For the first model, the explanatory variable x is not correlated with the error term mu1. However, X is correlated with the error term mu2 in the second model. Next, we use real-life data to verify that the variance of the OLS estimate will not be the smallest if the homoscedasticity assumption is not satisfied. Here is the sample for the US workers collected in 2017. We have used this sample before. We regress their hourly wages on the years of schooling. The graph of the residuals versus predicted values shows heteroscedasticity, indicating that the homoscedasticity assumption is not met. Suppose the error variance increases with schooling. We can use the weighted least squares method to estimate the model and obtain estimates with smaller variances or standard errors. Here's the method of weighted least squares. The OLS estimates standard errors are no longer the smallest when the homoscedasticity assumption is not satisfied. The weighted least squares estimates have smaller variances. Today, we explore the best linear unbiased estimator, blue. The OLS estimator under the 5 Gauss-Markov assumptions is a blue estimator. That is, it is the linear unbiased estimator with the smallest variance. We also demonstrated with examples. Thank you so much for watching this video. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.